Okay. With any sort of series question, you need to know how they work. A geometric progression you get from one term to the other by multiplying by a constant value. So you have your initial value. In this case, the first one is going to be a, and then the next one is a multiplied by a common ratio, so it'll be a times r. The third term will be a times r times another r, so ar squared. And in general, the nth term will be a times r a second time times r a third time, and so on. So it'll be a times r to the n minus 1, because the first one is obviously a times no r, the second one is a times r to the 1, the third one is a times r squared, the fourth one is a times r cubed, and so at any point it's a times n minus 1 lots of r's. This makes sense in terms of finding the 20th term, because we know that it's going to be the initial term times r to the n minus 1. N will be 20 here, so it's going to be ar to the 19. But obviously we need to know what a and r are. For this one, the first term, a, is clearly 4, and then what are you multiplying 4 by to get 2 and 2 by to get 1, because that's what you do in a geometric? Well, fairly obvious, it's a half. So we know that a is 4 and r is a half. If we substitute that back into ar to 19 for part 1, we get sorry, 4 times a half to the 19, which you can work out. But what makes this question slightly difficult is that once the answer is a power of 2, the way I would do this, if you're trying to write 4 and a half to the 19 as powers of 2, is to write the number 4 and a half themselves in terms of powers of 2. What is 4 as a power of 2? It's 2 to the power what? And what is a half to the power of 2? As a power of 2. 2 to the what is a half? What's the reciprocal of 2? So it's 2 to the 1. So this is 2 squared times 2 to the minus 1 to the 19. I've just replaced the half with 2 to the minus 1, which is the same as 2 squared times 2 to the, well, a to the b to the c. We take those two numbers and multiply them together. So this is 2 to the minus 19. And if you've got 2 to the 2 times 2 to the minus 19, you just add the powers. And so this is 2 to the 17. And that's your answer to part 1. Question 2. Let me just mark out which is which. For question 2, we need to find the sum to infinity. Is it worth going through the general principle for the sum of infinity of a geometric? Probably. Works like this. If a geometric which goes on forever looks like this, it says its first term is a, second term is ar. Actually, no, I'm doing the sum to n terms, sorry. And carries on, and you know that the last term is ar to the n minus 1. If we then take that sum to n terms, so a plus ar squared, blah, 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 that's adding up all the terms in the series, and we multiply them by r. Well, the first term, if we multiply it by r, becomes ar. The second term, if we multiply that by r, becomes ar squared, and so on. What we get, though, is that obviously the second last term on this would be ar to the n minus 2. If we multiply that, we get ar to the n minus 1. And if we multiply this by n, we get ar to the n. The clever bit is that if we take these two series, which could be extremely long, and we subtract the first one from the second one, so we do rs take away s. I can factorize that, I'll do that later. If we take away the top one from the bottom one, then obviously all these terms in the middle will cancel. And all we're left with is this one, which doesn't have anything which would bounce it out from the top, and this one. So it's going to be ar to the n minus a. Now both those can be factorized. Rs minus s is the same as r minus 1 times this is big S for the sum to n terms. And if we take the a out, we get r to the n minus 1. I don't know why I did the normal one there, but no. Anyway, what we get is a times r to the n. R's and n's look the same. R to the n minus 1 over r minus 1. Now that's the sum to n terms. I can write Sn. If we want little subscript n of a geometric. Oh, has that gone off the page? Ah, Muko. Right. Sum to n terms is a times r to the n minus 1 over r minus 1. There we go. Sorry, that disappeared. Now, let me just pause a second. Okay, now suppose this isn't the sum to n terms, but the sum for an infinite series. Well, obviously the formula is exactly the same. It's this, except n is infinity, so it's going to be a times r to the infinity minus 1 over r minus 1. But you say r to the infinity will be an extremely large, infinitely large number. Well, that's true unless r is between 1 and minus 1. You have to remember that it could be negative as well. If r is less than 1, then as you keep multiplying r by itself, it's going to get smaller and smaller. If r is, for example, half, then half of half is a quarter, half of that's an eighth, half of that's a 16th, half of that's a 32th, half of that's a 64th, and so on. You're getting smaller and smaller. And so if you keep doing that an infinite number of times, eventually you're going to get 0. The same is true for a negative number, although it will flip between negative and positive, but eventually it will turn to 0. So assuming that the modulus of r is less than 1, then this becomes a times 0 minus 1, which is going to be minus a over r minus 1. Now you can multiply top and bottom by minus 1. Minus a becomes a, and r minus 1 becomes minus r plus 1, or 1 minus r. That's an r, by the way. So the sum to infinite terms is a over 1 minus r, which means assuming that the modulus of r is less than 1. Now we already worked out that r was a half. It's been obscured there. R is a half from the first part. So in this case, our sum to infinite terms is a over 1 minus r, which is 4 over 1 minus a half, which is 4 over a half, which is 8. And that is the final answer. Apologies for the mess.